Welcome back, everyone, to day 2 of cybersecurity with Python and Microbit. So today we'll start off with some questions and answers. Then we'll actually do some review. I'm going to add some review to the questions and answers. We didn't get to radio basics yesterday, so we'll do that before moving on to radio data encryption, sniffing attacks and defenses, and brute force attacks and defenses. And then I'll talk about your homework, which is pretty short. And then on Friday, we're going to have a guest speaker from cyber.org who is going to show you a number of things, a number of curricula that they offer, including some block-based programming and also their cyber range for having for a safe way to set up computer networks to experience and understand how one computer can hack into another. And so that should be let's see here. Anything else to say about Friday? Friday we'll also finish whatever we didn't get to in which I'm assuming is just going to be possibly part of the brute force chapter. Okay, so first up, the homework was to have your microbits connected and communicating over the terminal. So microbit A, I typed, can you see this in? And as soon as I hit enter, microbit B shows me, can you see this? And then if I switch over to this terminal and say, yes, I can, then microbit B sends it out over the radio, comes in microbit A forwards it back to its terminal. And just a quick heads up about this. If you type something that is too long, it will be truncated. I want to say it's 29 characters, but I don't remember. The default buffer is 32, and that can be increased. Okay, so do you all have that? Do you want me to paste in the code? I'll just paste in the code anyway in case anybody doesn't have it. Let's see here. Close serial. Copy. Okay, so I'm going to first paste in microbit A. There's not really much difference between microbit A or B, but it'll be nice to still have them differentiated. Oops. Okay, so here is microbit B. So anybody who needs to get that loaded into their microbits, go ahead and do that now. If you need to get both your microbits connected, remember that when you hit the connect button, well, I'm already connected, but when you hit the connect button, it'll present you with 2 microbit options if you have both connected to the same computer, in which case you'll need to choose one of the 2 for one of your Python editor tabs. And then when you connect the other of the 2, you'll need to select the other option that's in the list before clicking the connect button in the dialog for your second microbit. And let me see if I can find a picture of that. So basically, when you hit that large connect button, you have 2 microbits connected, you'll see a list of 2 microbits, each with its full machine number displayed. And what I usually do is I try to look at like the last few digits, because that's, it's pretty easy to see the difference. So I like when I was developing with these two microbits, I just said, oh, well, I've got microbit A because there's the last non-zero digit is an A. And then I called this one microbit 8, just to differentiate them when connecting. Okay, getting back to today's slideshow. Okay, so have we all got our chat going? Can I get some thumbs to see where we're all at? Okay, good. Anybody who's not visible, click or tell me you need some time. Click your thumbs up. Okay, got some thumbs up, got a few thumbs up. All right, way to go, everybody. Okay, then. So if you're still scrambling to get your chat running and need some more time, just unmute yourself and ask me to hold up. Otherwise, I'm going to continue. So back to this, we have these two microbits that are doing their chat, and the chat works pretty nicely. Now, this is one of 2 applications that we go through all the cybersecurity lessons with to give an example of, hey, this is something where encryption can be applied, because this is wide open communication. So if you imagine that microbit A, now in a classroom, this works really well because you can put folks in groups of 3. You can have 2 people doing the chat, and then another student doing what you would call a sniffing attack, and silently gathering information on the chat. I've noticed that students also like to do DOS attacks, that being just typing in a whole bunch of stuff over and over again so that the other students can't really get anything done. And so those are 2 common attacks, cyber attacks, that can be emulated with this chat application. And for the sniffing attack, I'd just like you to think about
Andy, I lost your audio.
Actually, I was just doing the war games text appearing.
All right, you got me.
So the idea here is let's imagine for a minute that microbit B is, the lesson is, this is wide open. It's not encrypted at all. So anybody can see what you're typing. So when student A maybe says, I'm in a bad mood today, sure, maybe they intended to tell that to microbit B, but there's potentially a microbit C, D, E, F, and G that could also have gotten that information. So I'm fast forwarding quite a ways here. And so what I'd like to show you is the encrypted version, which is a few chapters ahead in cybersecurity sniffing attacks and defenses. And the code is bear with me a sec. Texting with terminals encrypted versus unencrypted. So here is one way to address a simple sniffing cyber attack. I'll paste this in a second. First, I'll demo how it works to you. So this one has something called an ASCII shift cipher, and I'm going to rewind and talk more about this. But I thought I'd kind of show you right out of the gate where some of this is going. So if I flash this and then go to the terminal, notice the first thing it does is it asks me to enter an encryption key. And in that particular example, they're suggesting 19. So I'll go ahead and type in 19. And so now we're assuming that another student who also entered their encryption key to 19 will be able to understand the conversation, but any sniffing attacks like this microbit B cannot. So what we did was I just put the encrypted code into 1 so far, and I will have you do that in a second. So test message. Okay, so TEST space MESSAGE came through as GX, open, close parentheses, et cetera, et cetera. So basically, it came through as something indecipherable. And this is one of several examples that we're using with and without robots. There's a robotic option for all of these too that I'll show you more about with the Cyberbot robot on Friday. So here's an example of encryption to foil a sniffing attack. And then, so what we can do next is basically load the same thing into our second microbit, except for we want to call it transceiver B. And then we can flash. And then enter our key, and we want to enter 19 since that's what we did in the first one. And then we can say, how about now? Question mark. And sure enough, it is being decrypted. And you see this question mark? Yes, I can. All right, so those are so first off, we emulated the sniffing attack on the open channel, and as soon as we encrypted the first microbit, there was nothing sensible coming through the second microbit. Then update the second microbit with the encrypted version and enter the same key, and then we're back to being able to see each other's messages, even though somebody who is just using the open channel cannot see it. All right, so with all that said, I would like you guys to try that because it's kind of fun. Chat. Okay, so here is the okay, here is the encryption version. So put that first into one of your editors. Run it, give an encryption key, 19 if you're, but really any value will work. And then go ahead and verify that things look pretty weird when you're trying to chat with the second terminal, because of the fact that the second terminal, which is currently a sniffing attack, is being foiled and it's seeing the encrypted data. After that, paste that same code into your second microbits editor, load it into your second microbit, and then go ahead and enter the same encryption key that you entered for the first one, and then verify that now your microbit, which shares the encryption key, is able to see the unencrypted version of the text.
Andy, is it possible for that encryption key to be alphanumeric as opposed to simply numeric?
Let me think about this. Alphanumeric. Oh, I see what you're saying. It's possible. One of the places this is going is we offer several examples of increasingly hard to crack keys. And the reason for that has to do with brute force attacks, that we start out with kind of, pushover ciphers and then gradually up strength. And so for those of you watching along on YouTube, I'm just trying to make sure that everybody has enough time to try out that example. So if you could, once you've tried both the encrypted to unencrypted and then encrypted to encrypted chats, go ahead and give me a thumbs up so I can monitor and decide when to move on. Good job, Alan. Alan, you can definitely do alphanumeric keys, but this particular cipher has the second most simplistic cipher that we're introducing, and that particular cipher, I think it might actually, if you tried alphanumeric, you might actually get a runtime error. Your microbit might call because it does not have exception handling.
Correct. Currently.
Currently, yes, it can certainly be added.
Andy, there's a question for you in the chat about
Oh, thank you.
showing the code.
Let's see here, where did the chat go? There it is. Can you show the code in the python.microbit.org editor? Yes.
Yeah, if you can just close, thank you.
Yeah, so here we are. And then let's see here. Zoom out just a bit.
And I think that's the code that you pasted in the chat a couple of
It is.
posts prior, right?
Yeah, now would you like me to repost this code? I can certainly do that. Another thing I can do to make it more legible is what I'll do is I'll zoom in on the upper part here. And then I'll show you the lower part. And I'll also shade where, so we have key right there. And then that is this line 29, so you can start from line 29 and go to the bottom. There, is that properly, or is that visible enough for you?
Looks good to me. It's pretty legible.
Okay. Some of you may have 13-inch monitors. I hope it's still legible at that level. I don't know how much monitor real estate you have, Jeff, but I'm guessing it's somewhat more than that.
Yeah, plus I have 3.
Yeah. Oh, that's right. Do you still have the same 3 that we talked about before?
Yes,
Oh, awesome.
they're still working.
Yeah. So is that kind of like a vanity where you have like a main monitor and then 2 small ones on the side?
That's right. Yeah, main one in the center where I keep my focus most of the time, and then 2 auxiliaries, one on each side.
Jeff is our senior software developer, and so he makes, I'm sure, quite a bit of use of that space.
Yeah, debugger on one screen, running application on the other, and some documentation on the third.
Yeah, or code.
Yep.
Oh, I guess that would be the debugger.
In the debugger, yeah.
You know, if
Okay.
your code were perfect, you wouldn't need that other monitor then.
That's right.
So
My
friend-
code is hardly ever perfect the first time.
Yes, and Alan, you know, you mentioned me buying beers for everyone after botching my thing on objects. Well, don't write code after that though, because you'll get cited for drunk deriving. But
dun.
all right, so everybody, do we Stan, I saw a nice round end shape there. Okay. All right, silliness aside, have we all tried the different versions? Okay, I'm getting thumbs up. All right, so I kind of wanted to give you sort of a preview of where this is all going before climbing into the details. And to climb into the details, I actually want to make sure not to have quite, we went through some of the material pretty quickly yesterday. So I'd like to back up and just do a second review of the things we talked about. And pardon me while I back up to the right spot. Okay, here we go. So the first thing I wanted to mention is that there are things in Python called lists and tuples. Both are basically lists. It's just that a tuple is enclosed in parentheses, whereas a list is enclosed in square brackets. They both can have the same kind of information. The only difference is that a tuple is considered to be, or is called immutable in Python or code speak, which means that you can only access these elements. You can't jump in and change them. So tup of 2 accesses the 0, 1, 2 element high. So that's why we see high right there. Tup of 2 equals high. Then you can also do that same thing with lists. You could say list of 2, and you would end up seeing high. But with a list, you can also change its elements. So by doing list of 2 equals 5, notice that we displayed the whole thing. Well, we displayed the whole thing first with high. Then it's printing that we're changing it. So then we see the whole list with that by element changed. And then the last thing we're doing is going and getting lists of 2, and it shows us by. So this is a way to keep lists of items and also access, and in the case of actual lists, the ones in square brackets, change them. And then remember, we used music as an example of a practical application of list, as well as a shape the microbit and find out your next thing to do application. Dictionaries are the microbit version of JSON data, which is used transferred between web pages and servers quite a lot as you're using your web browser. It's it's one of the ways that data is transmitted. And the important thing about it is that the elements of a dictionary are arranged in key value pairs. So there's a key, name, and a value, Sir Lancelot, and then a second key, score, and a value, which in this case is 1,000. And you can do things like say, hey, this dictionary enclosed in curly braces is named info. After that, you can say info of score and you can change it by saying info of score equals 1, 2, 3, 4, or you can get whatever value was in there before by saying number equals info of score. And then I think we actually did this. And basically, if you want to try it, just keep in mind that the code example is here for you to try. I'm trying to jet through this because there's a lot of material to cover, but I do want everybody to feel solid on these elements because I'm going to be mentioning where they are in the data exchanges and encryption stuff. Okay, then we get to exception handling. And exception handling, it's funny, I just said that, but I really want you to try this one because it is super important. Yeah, I think having a hands-on experience with this is going to be really helpful. So I'm going to paste you in the link, and I want you to run this and verify that it does the 20 divided by 5 division calculation. Then I want you to try changing D to 0 or change D to ABC in quotes and see what happens with your microbit. So I'll do that first. Just to show you how this is going to work. Okay, so we'll take this script here. And I'm going to paste it into one of the editors and flash it. And then opening serial, we see that 20 divided by 5 is indeed 4. Great. Now, what we'll do is change that denominator of 5 to 0 and flash it. And then open serial. And basically, the microbit halted right there, and it's not going to do any more of its script. So imagine a robot trying to roll around, and all of a sudden it has some kind of exception because it's receiving data that it wasn't expecting. Well, the robot will become unresponsive. So that's a thing that is important in the microbit and web browsers to deal with, is to set up exception handlers so that the unexpected won't damage your code execution. Okay, with that said, I would like you to try, with that said, I'd like you to try that. And so chat is on its way here. Paste. Okay, so please try that out first, unmodified, and then modified to 0. And by the way, this is coming straight out of the book here. But and so the students would be doing this kind of thing step by step. All right, is it true? In order to change update information within a tuple, the tuple must be changed to a list. Alan, I'm not sure. I'd have to test that out. It may be that one tuple is discarded and a new tuple is created automatically, or it may be that you have to move the tuple to a list, change the element, and then, well, essentially, when you say, that the new tuple equals the modified list, I know at that point the old tuple will be discarded and it will be replaced with the list of the new tuple. So
that's my understanding of it also.
Okay, thank you, Jeff.
I haven't tried it.
Yeah, me neither. But in terms of getting it to work, it's a little bit different. Let's see. Okay, there's a W3 schools page about it. Thank you. I'm gonna skip W3 schools pages because they sometimes make my browser run slowly and my CPU fans start to scream. And I think it's already under enough stress. So, folks, how did that go? Did that work out for you all? So we now have a situation where we have an exception that needs to be handled. So now we'll take a look at adding an exception handler. So this is the same code, but embedded in try, which is code that we think might have a problem. I'm not sure, but we'll try it. And then if there is an exception, in this case, we're just printing the exception. Now, if there's not an exception, we'll print the result. And then finally, we'll just prompt the person to rerun the program and try again. So this is the next one. And I'll just have all you guys try it at the same time that I try it. Paste. Okay, so this one is in your chat. Now, try pasting that one into your editor. And then repeat the same thing of starting with it unmodified with 5, and then changing the denominator after verifying that it works to 0. So check your chat, should be in there. I'm gonna flash this. Oh, unless I chatted it only to Alan by accident. Let's see. No, that went to
Just to everyone.
Good. All right. So flash, open serial. Okay, so it works the same as it did, even though it looks like a lot more code now. And then when I change 5 to 0 and flash it, I see a message that there was an exception, but to also try again, which means that that the microbit did not halt all code execution. It did not choke on an exception. It let me keep going. So that's the key lesson of exception handling. Okay, can I get some thumbs to see if you finished? All right, looking good, everyone. And again, interrupt me and say, could I have 30 more seconds if you need it? All right. Now, exception handling, another thing you know that this chapter has the students do is understand that there are different kinds of errors that are generated depending on the type of exception. And then they are challenged to modify their code to give a helpful message given a particular error. So, you know, to tell people you can't divide by 0, or that, you know, it expected a number when you typed hello as a denominator. Because this is now using allowing you to type numbers in repeatedly. The application grows and the students type in numbers and they see the results and etc. Okay, then strings. So did anybody try the homework? Oh, good job, Alan. Could you get it going?
Oh yeah,
Okay, good.
I got addicted.
Yeah. Yeah, so I also tried the homework. Surprise, surprise. And I kind of didn't like my first solution, which is sort of the student's solution. And so I'd like to talk with everybody about a solution that so this is the solution to the homework. It's the 4th slide into today. So 1, 2, 3, 4. So this is the solution I did during the previous security workshop. And but I modified the code a little bit. Let me just make sure it works. Flash. Okay, I think this is the right one. I was kind of last minuting this, sorry if somebody finds a bug. Let's see here, chat. Paste. All right, so essentially, if you run this, you're going to see a bunch of results that really don't make much sense if you're just staring at the monitor. So what I did was I've got them side by side now. So here is the code. S equals 1, 2, 3. That's creating a variable that stores a string. N equals int of s. So now n, because of the fact that this string actually stored an integer value, n is going to become the value 123. Now, n equals n plus 1 means that n is going to be 124. So if we print the value of n, we see 124, even though we started with a string that was containing digits. Now, then here's another string. It's much longer. This is a string. A string is a sequence of characters, I believe is what it said. Yes. And again, this is from the online textbook. Then we print string, and so here it says string equals. This is a string, et cetera, et cetera. And so these are examples of methods that come with the string object. So this string here, even though we think of it as just the stuff between the quotes, a string also has a lot of functions and methods that you can call that pertain to it. So one is string.find. So string.find sequence. Well, here is sequence, but where is that in the string? Well, it's going to be in car index, and we see that car index is 27. And so looking at this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 20, 1, 2, 3, 4, 5, 6, 7. Yeah, it's the 27th. So the word sequence starts at the 27th character in that string. There's also string.replace, where after replacing it with a string, notice that instead of it is a sequence of characters, it now says a string is a sequence of characters. And then we have the string lower and string upper, which simply give us that string as upper and lowercase characters. So that was something that I really wanted to show you. There's a lot of things you can do with strings, and and this pertains a lot to the encryption that we're going to be doing. The one last thing I wanted to add would be this. Let's see here. ASCII equals board of A. I'm freestyling here, so sorry, this might not work. Print. Okay, fingers crossed. Ah, yes. See how it says ASCII val equals 65. So that is the ASCII code for A. I mentioned that. I don't remember where it was, but I wanted to mention that that you've got board, and then you've also got I think it's car.
I don't think there's an A in it. I think it's just CHR.
Thank you. Yeah, I know that the syntax changed from white to green. There we go. Okay. So these are now, okay, so the string dot this and string dot this are methods. These are functions that do operations on strings. Flash. So this is the number 65 converted back to an A. So ord and char are two examples of functions that work on strings. And there's an entire chapter that talks a lot about strings, and the students do a lot of hands-on stuff. Okay, next up is radio basics. So let's see here, time-wise. So we did texting with terminals already, and that's good. So I guess at this point, I think I'd just like to point out that texting with terminals was quite a ways into the chapter, and that there's a number of experiments that lead up to it. So the first is it opens with some informational stuff, like take a look at your microbit. It's not going to be exactly the same. If you can see my thumbnail, here is the antenna for your microbit radio right there. On the version 2, they put it at a diagonal as opposed to right along the top. And then the Nordic RF 51822, which is probably slightly different on the newer microbit, and I cannot read that tiny writing. Yeah, it's going to be a slightly different number, but basically the radio still works the same. So it's the radio wave oscillates at 2.4 billion times per second. And so these are things that we explained to the students at the beginning of the chapter, that the 2.4 gigahertz band is for Bluetooth and Wi-Fi, but also, and since it's a Bluetooth radio, that makes sense. Then for the Gazelle protocol, if we're using the microbit to communicate like we did using the chat application, where we typed in the terminal of one microbit, it sent that data over radio to the other microbit. Then the other microbit, I probably should switch to a, I'm going to come back here and just switch to a, okay, so essentially what was happening when we were doing that chat, which I wish I had said at that point, is that we have one microbit, we're entering text in the terminal. The terminal, and that text, when we hit enter, it ends up going over the it ends up getting converted to USB, goes over the USB cable into the microbit sends it out, and then it is received in the second microbit's radio, comes back, and then the second microbit sends it to the terminal. And then if you type in this one, in this terminal, it goes the other direction and ends up in this terminal. And so there's a radio, so all this communication is happening between one microbit's radio and another. Okay, so back to the introduction. You have 83 different channels. So one initial move that groups of students can make for privacy with their chat application, for example, is to pick their own channel. But that's kind of thin, because any student can try surfing the channels and see see what other conversations they could become privy to. Now, you can set the power to max, and you can have 230 feet line of sight for reliable communication. The protocol we're using with the Bluetooth radio is not Bluetooth. It's called the Gazelle protocol. And one of the reasons this is nice is it makes all these examples of scripting your own ciphers for encryption completely doable. Next up, so then the students, as they're going through, I had you guys jump in the deep end, but the students get to see, okay, let's try, a one directional radio conversation first. And so we do sending radio messages. And so there's a script, and the idea is to keep the script manageable, to have it be something where it's not overwhelming. Of course, they've been doing quite a few scripts, so by now, this is, although longer than some of the scripts they've been working on, it's still fairly short. And they learn about turning the radio on, setting the radio's channel, and then using radio.send to send out the message. And then on the next page, they learn about using radio receive to receive the message. And oh, this is funny. I thought I changed all of these. I believe that if message works just as well as if message is not none. That's kind of a double negative. So basically, it would be more clear to say if the message exists, then print it. Otherwise, just go back and keep on checking with radio receive to see if the message has come in yet. At any rate, so the idea is that they learn that that they can import radio, turn it on, set the channel, and either send or, in this case, receive, and then how to repeatedly check the receive, whereas just hit send whenever the application needs to send. Then texting with terminals. So they even start with unidirectional text. So they start with one-way texts that are basically testing to make sure that the sender can send the message and then the receiver can receive the message. And then we did bidirectional texts, and that catches us up to part of it, the part before it was encrypted. Now, before moving on to encryption, there's one more thing, which is radio data. Radio data, so just a string is well and good for exchanging texts, but devices like the Microbit can also do embedded applications. And so if you remember, we did an application on Monday that was a countdown application. I think we'll see that in a minute here. Okay, so let's talk about radio data very quickly. Radio data is where dictionaries come into play. So here is that same countdown application, except for now you're typing your number of seconds to count down and the thing to declare after the countdown is done into your Microbits terminal, and then it sends it as a dictionary. So remember the things, and remember a dictionary is a group of, I can't get that any larger. It's a group of key value pairs in between some curly braces. So seconds, :3, and after, :liftoff. And so it needs to be, so the receiving script needs to parse that dictionary after receiving it and then do the liftoff. So this is as fundamental of an example of an application of something that's doing something for you with the microbit. So there's text, that's one thing we want to protect, and then there's application data. That's another broad category of things we want to protect. So let's see here. And so let's see, let's try that out. So here is countdown sender. We'll have you put this in one of your microbits. Chat. Okay, so that is countdown sender. I just chatted it to everyone. And we'll put that in one microbit. Okay, so select all, paste. Okay, so there is countdown sender, and then the receiver script, countdown receiver, we'll put it in the other microbit. So here it is in the chat. All right, and if everything works properly, you can flash both of them and then hit the open serial button in both of them. Now, one of them will, you want to go to the sender one, and it's going to tell you the same thing it did on Monday. Enter the countdown start. So we'll count down for 4 seconds. Or whatever number you choose. Choose a small one so you don't have to wait long. And then it says enter message after countdown. And so kaboom. Now that got sent over the radio, and it got sent as a dictionary, and it parsed those values. It said, okay, let's go find the after value or the value. Well, that's start, and the number was 4. And then let's find the after message. Okay, so that's kaboom, and then it went through and did the same thing. So this is basically the 2 microbit version where you're typing the data into one, and then the other is executing it. And I wish I could have, I wish I thought to just type in liftoff again, because this is an example where with a little bit of extra code, you might have a remote model rocket launcher, or a remote, I don't know, insert your, your students will have a lot of ideas on what they might make that can be remotely triggered by sending data to an application. Everybody got that running? Okay, I saw a head shake, so let's wait, and feel free to unmute yourself if you need some help. Let's take a second for questions and comments while we're at it. Okay, thumbs up. Good job, everyone. Let's see here. We're almost at break time. Let me take a look. Actually, we're at an ideal break time because we're going to start with encryption. So let's take a, let's see here. Let's take a 7-minute break. You could all come back at 5 past the hour.
Andy, you were mentioning with one of the courses as we're talking about the cyberbot, that I'm assuming that this is kind of an example of where you get into the encryption, that you and I both have a robot, but I set my encryption to 19, yours is set to 43 or whatever. So when I send turn right, turn left, it's not affecting you. And likewise, you're unable to affect me because your commands can't come through other than as gibberish.
Yes, that is part of it. There are some other parts, which is, first of all, you can select a separate channel, a separate radio channel, but then, you've got cyber, you can end up having cyber attackers who, first of all, they find the channel that you're on. Well, now, you know what? I forgot to mention frequency hopping when we were, there's an example in radio basics of frequency hopping. So that's where the sender and receiver are in lockstep and they're jumping to various different channels, but not staying on one forever. And so
you're talking about, I send a message and then we can hop. And if mine goes from 13 now to 14, you're going to go to 14 with me because I've sort of sent, here's the new hop.
possibly, or it can be a pre-arrived at sequence.
Yeah, I wrote some code for my students with which to experiment with radios, where first they just kind of got a bunch of code and it was random and they had to figure out, they're sending out a message. If you got a message that was a smiley face, find all your smiley face buddies. So they would go and hit, a button and they'd be able to, transmit so they could see, but a smiley face only went to this group, a sad face went to that group, meh went other places. But then I started to do it with using the A or B button to increment, or I can either increment my my channels 1 through 10, just as an example in class, or it could also go with a random. So they just found a new group, and it was interesting to watch them run around a little bit like roaches in the light, trying to find their new partner on a new frequency. And
that is really awesome, Alan. Would you mind, I'm actually thinking that would be a really cool thing to add to these. Might I do that and give you some author credit there?
yeah, it'd be my pleasure.
Okay, that's great, because I really like that. And I think the students are going to enjoy it a lot. Okay, excellent. Let's see, I got, so with the robots, there's some other interesting things that can happen. One is, if you're sending data to your robot, and another student sends incorrect data on the same channel, without exception handling, your robot is dead in the water.
Correct.
So that's where so essentially a very simple cyber attack is just to cause a server or browser to freeze when by supplying it with data that it's not ready to handle. So that's one thing that can happen. So they have to harden it against attacks by adding exception handling. They also have to harden it against attacks or against sniffing attacks by encrypting. And so these are all the different, when it all comes together at the end, and the students are in a robot contest where they're trying to get to a goal, and another group of students is trying to either trying to prevent them from getting to that goal. There's the more that they're able to incorporate from the lessons that they've gone through, the better of an advantage they'll have. And so, yeah, the robot, with that in mind, does and especially with a contest in mind, does take this to essentially another level. Because all of this fits into the Cyberbot robot, and it can be applied in a contest, and the students can really test their mettle. Still got a couple more minutes. Anybody else? Comments, questions? You too, Alan.
So Andy, we had a question and Alan is also answering there, participating there.
Okay.
Because with this back and forth, entering values and printing in the terminal, sometimes it blurs the lines of where the code is running. Like if it's running on the computer, it's running on the microbit. What happens if I disconnect the microbit? Which in this case, the code is running in the microbit, but you are using the PC as a terminal, so you have to be connected unless you show the values on the display. But they are kind of strongly integrated, so I think it gets a little blurry of where the code is running.
Oh, I see. Yeah, that's that is one of the reasons why we use. Okay, so there's a few things about that. One is that later on there are some microbit only examples, but notice the concept diagram here that it shows that there's and this is also accompanied by words in the chapter, but the concept diagram always tries to show, hey, look, there's USB communication happening in two directions here. There's radio communication in this example happening in two directions. Now, if we go to an earlier example, there's USB only getting sent to the terminal, and there's radio getting sent in one direction. So we add concept diagrams to each example. And I also want to emphasize that we're really skipping through this at kind of a furious pace in a 6-hour workshop. And so my hope is that the students will have the chance to approach this in a more following the step-by-step instructions, methodical approach. And hopefully that will help. So that's one thing about blurring the, potentially having some difficulty understanding what's doing what. And then the second thing is that we will have some examples where you can go with just a battery later on.
So Andy,
Yeah.
I have some problems where I still have not got my microbit to actually display anything. My terminal does. So when I'm on the computer, it's showing everything that I programmed in, but I still don't get it to display on my microbits. But when I did the tests practice from the beginning where you had to post the A and the B, my A and B do go to my microbit.
Yeah. So,
and I know students will have that problem. So what are some debugging things we can know as a teacher? Like, what do we check? I've switched my browser. I got my computer plugged in, charging. I've got batteries hooked up. I'm like, what else can I do?
okay. So the main thing is just the, let's see, where would I go to answer that? Okay, so learn.parallax.com. And so Python, cybersecurity. Okay, so we have two approaches. We've got writing microbit programs, uses one of the approaches. And then computer microbit talk introduces the second of the two approaches. Try to get these tiled. One of the things about a Mac is it's difficult to tile unless you go and get a new app. I'm not always crazy about adding apps for stuff. Windows, you can just kind of smack each window against one side or the other. All right, so here is the LED matrix intro. And so notice that here it says display.scroll hello. And there's also display.show. So those are the two main ones for like count and repeat. Let's see if I see any. Yeah, they really depend on display.scroll quite a bit here. But display.scroll and display.show are your two main tools for sending data to the Microbits 5x5 LED matrix display. Whereas input is a way to enter values into the terminal and get them into the Microbit. And then print is a way to print to that terminal. And so I've been, as much as possible, focusing on the terminal, because another thing about, you know, another consideration with cybersecurity was simply that a terminal is a very heavily used tool
Right.
in networks and cybersecurity and stuff like that. So that's why the majority of the examples are using the terminal.
Oh, so it really shouldn't be displaying on my microbit.
That's correct. Yeah, it
Here
should
I'm
only
thinking I'm
be.
doing something wrong. I'm like, why is it not displaying?
Yeah, so here's the thing. If your students want to change their application so that they can see message, all you have to do is change.
Yeah, I get that now. I thought I was doing something wrong because I totally understand terminal and all that. I don't know. I thought it was really supposed to be showing on the microbits, and I'm like, why is mine not working?
Yeah,
Diane,
no, I apologize actually, because this question has come up at least 3 other courses. So I forgot to mention that and be really clear on that one.
Diane, was during the break part, we're saying that that's something that I do within my code a lot, whether it's C, Python, whatever, is I want that. But on the microbit, where you can see on the right screen that he's got where it's the print message, prints within the terminal, I'll take that and do display.scroll, open parentheses, message, close parentheses. I typically use scroll over show because I want something to scroll across. If you have a word like hello and you do show, it does H-E.
Yeah, yeah.
You don't know, but when I have it go and scroll, and that'll give me my visual as well. So I've got my terminal, or like Robert was saying, if I disconnect and now I hook it up with my battery pack so I can take them somewhere and play games, then, you know, at least I know.
Yeah, because I've programmed in my computer science class, we've programmed microbits before. I've never used it in my cybersecurity class. And I could see that disconnect with the kids and saying, wait, why do we need a microbit then? Because if it's running in the terminal, like what's the microbit for? And that's what I was sitting here going, why do we have the microbits connected? We're not doing anything in there. But I get if I would throw that in then, Alan, that maybe the students would see the connection to where that microbit is coming into play then, is actually just displaying it there.
Well, one thing I would maybe add for my students in that case, Diane, is that in fact, we are using the microbits there because the Python is running on the microcontroller itself. We're using our computer just simply as a monitor because we can see more stuff. So if you relate that from a microprocessor standpoint or other types of integrated IoTs, your refrigerator, for example, doesn't have, generally speaking, I know the new ones do, a monitor. My Jeep, you know, when I hook up something to my OB2 connection, it gets a connection and I'm using the microprocessor on my Jeep, but I'll read that out on something else. So
yeah, and I think that's where my kids always got confused, because like when we program in Python, all you do is see it on the screen and they're like, so like, what's the difference then? They're not getting that. They're seeing it on a monitor, but it could be displayed on anything else, a TV, a refrigerator, or whatever else.
Yeah, so one of the things, when they're using the Cyberbot robot, both of those come together. Because you'll have one microbit connected to a computer and you're typing in, for example, navigation information into the computer. And then that gets zapped over to the microbit that's on the Cyberbot robot. And then it parses that message and acts on it.
Okay, yeah.
And so these lessons were peeled away from the cyber. So the Cyberbot was developed as an entirety. And it basically just occurred to us, hey, you know, lots of people have microbits and they might want to do a condensed version of it. So we peeled away the cybersecurity related stuff from the Cyberbot and made it its own thing, which is what we're doing. But there is a version where you go through some robotics initially too, and then come back around to yeah. All right, let's see. So next up is oh yeah, that's right. There's one thing that I forgot to mention in radio basics, and that is that we talk about a technique called frequency hopping. And frequency hopping is when you use by the way, there on the previous page there was some just more information about radio frequency. But this is a script example where the sender initially sends some data on channel 7 and then switches to channel 14. And then the student is challenged to write a script that can catch both of the messages. And that is and it's introduced because frequency hopping, when your Wi-Fi is communicating with your computer, your Wi-Fi and your computer do jump around to different frequencies within the band. And so that is frequency hopping, and it's a way that was initially used to add security to radio communication. All right, so on to sniffing attacks. So let's look at an example that does use the 5x5 display. And so this is the share something personal light version, where instead of chatting about what you're feeling, you just might use a button to select one of the Microbits images. And so this is the send images application, which I'll paste into you. Uh-oh, what just happened?
We got big.
Yeah, that means that I accidentally stopped the screen share.
That's right.
All right. There everybody is. Share screen. Okay. Now back to sending the chat. So this is the send image script, and then the receive image script is right here. And this is all, again, a second example of unencrypted. There's the receiver script. Okay, so I gotta go and grab the sender script again. I'll just paste in the page as well in case it's easier for you guys to do it straight from the page. All right, probably should have done that earlier. Here is the transmitter script. Copy it. And paste it. than the receiver script. Okay. And I flash them both, and I don't remember, yeah, okay, so just a side note, in these scripts, I believe that I'm printing, oh, that's funny. Let's just see what's happening here. So the sender, yeah, so it is saying what it's sending in the terminal. And it is saying what it's receiving in the terminal, but
Not sending it.
the transmitter is on the left. Is that you guys' left too, or is my screen reversed?
Your send is left, your receive is right.
Yes, and so we can see in text and in this case with the microbit itself. So there's another slightly simpler example of communication to protect that is again over the radio. And you know what? I ended up skipping encryption entirely. Sorry. I skipped to attacks and defenses without talking about encryption. So let's see.
Andy, the image, unless mine is messed up, the image is displaying on my send, it's not displaying on my receive.
That's correct. Yeah, that's you can certainly use display.show to update the sender. Oh gosh, let's see, it's image dot. See if that works, or if I have a runtime error somewhere. Nope, wait a sec. Yeah, so there's a runtime error. What did I do? Image.happy, image.sad. Oh, okay.
Yeah, that works.
Yeah, and I think that's probably fair game to challenge your students to do that. But if you think I should just change the tutorial, we can do that too.
I like that there's always a going beyond, you know, a little bit like what Diane was saying and others that, you know, oh, so you want to see it? What a great idea. How would you do that?
Yeah, agreed. Okay. So, yeah, we need to jump back to encryption because what I was setting up there is just another way of protecting your data like we did with the chat. So let's talk about how encryption is introduced. Okay, so we start with just the really most basic of encryption, which is called the Caesar cipher. And this is a way of basically attributed to Julius Caesar during military activities. So if we have the letter E in hello, one thing we could do is pick a key of 5. And so for that, we jump over 1, 2, 3, 4, 5. And instead of sending the letter E, we would send the letter J. And so the word hello becomes the word MJQQT. And for decryption, all you have to do is go the opposite direction, starting with MJQQT. If your key is 5 and you're using the Caesar cipher, M, jump back 5 characters and you get your H in hello. Got to be careful when your key wraps around. So if you want your plain text to be X, you can go 1, 2, 3, 4, 5 to get to C. Now, for encryption, you remember where during the string, one of the string methods that we did went and found a word in the string. I don't remember the word, but I do remember that it gave us the number 27, that it was a 27th letter in a much longer string. So a nice simple way to do a Caesar cipher is to basically, this is actually introducing or reintroducing string.find, because that's what we use to give us, you know, the location of a word in a string. But in this case, the word is just a single character. And so after finding the index of that character, then we can move on to encryption. So first it introduces, just reintroduces using the index to find out, you know, how many characters into the alphabet the letter M is. And it looks like 12. Then the Caesar cipher encryption for a single character is simply done by saying, all right, well, if I can find that index using string.find, in this case, we named our string alpha, so it's alpha.find, then I can say, well, I know that the letter M is 12 in and that my key is 5. So we'll go ahead and say, we'll go ahead and get the index of M and then add key to it and give it a new index, this percentage sign I'll get to in a minute. And then the result is alpha of index. But remember, you can, with strings as well as lists and tuples, you can say object of index. And so if we have M plus 5, and that's 12 plus 5, so that's going to be 17. So it's going to go to the 17th character. So 1, 2, 3, 4, 5. And so I believe we'll be getting an R out of this. I may not have done that right, but let's just find out what really happens. Okay, so there it is in the chat. Let's see what happens. Yes, the result is R.
Done like a good pirate.
Needs to be followed with a G. Or at least I've always thought it as ARG. Yes, here we are, 17. Okay, so this is an example, and then we go into how does this actually work? And so we have our key of 5, our letter of M, and pretty much all the stuff I just showed you is explained here in a graphic and also explained in words above it. Now, how do you deal with the special case of when you have an overflow, like when you want to get ciphertext of C when you're choosing the letter X? And the answer is that the percent sign is the modulus operator. Now, with integer division, which is a double slash, 24 over 26 is 0 with a remainder of 24. Now 29 over 26 is 1. The integer result is 1, and the remainder, the leftover amount, is 3. And so if the script always uses that leftover amount, it will have 24 when it needs 24. It will have 20. It'll have 0, 1, 2, 3, 4, 5, 6, etc., all the way up through 25. But when we get to the 26th character and we want to wrap around, we get 0. 27th character is 0 for A, 1 for B, 2 for C, and 3 for D. So that is how that wraparound special case is dealt with in code, is with the modulus operator. Now we also have encrypting and decrypting with the terminal. And let's see here. Yeah, this is a pretty fun one. We'll go ahead and try a few encryptions and decryptions. It's basically just more code around the Caesar cipher. Paste. I try to do this step by step because throwing a giant gnarly script at the students is not really the best approach. Yeah, I see it says set your keyboard to caps lock, and without doing that, I got an exception in my application pros. So another example of why exception handling is important.
Could the input be set to upper?
Yes, absolutely, Alan. The to upper method that we talked about earlier to change everything to uppercase would also work. And that's, that's another good thing to challenge the students with, I think. Although I'm open to guidance on this, whether or not it should be something that is just added to the script. I try to keep the script simpler, and so in the instructions and then in the prompts here, it tells you to go caps lock. So if we enter a key of 5 and then use X, we get the result of C. And then what was the other one we used? Was it like M? Huh. Oh, I'm supposed to enter the key again. Enter key of 5. And if we enter M, we can enter a key of -5. And then enter the letter R. That'll get us back to M. And that shows how to encrypt. You can use the key, and to decrypt, you can use the negative of the key. Does that make sense? All right. Then we extend into words. Just to show another step. It's in the chat for you. Okay, I forgot to do caps lock again. Close serial, open serial. And you're supposed to enter the key. Not being very good about reading the instructions here. Enter the key 5. Hello is MJQQT with a key of 5. And then we can go in the reverse direction, entering the key of -5, then entering MJQQT to get back to hello, and that is another hands-on example of encryption and decryption. Are we all good? Okay. Next up, we revisit functions, because it's not really great to have to insert the Caesar cipher code anywhere you're going to do an encryption or decryption when you could actually just insert a function call. So here is the Caesar cipher with a function. And it basically does the same thing, I believe. Just, yes, let's see. So with this, you can enter the key and type in hello and enter a negative key to get the decryption MJQT again. All right, so the only difference here is that the Caesar cipher is sitting up here in a function, so that all your script has to do is call Caesar of key comma letters, and then the Caesar cipher returns a result, and that result gets stored in a variable and then printed. Before moving on to protecting your data, we have just a few other cipher examples, and what this does is it just kind of gives a simple yet still somewhat hackable approach, or but less. It's a stronger cipher, but not by much. But it allows you to take an incremental improvement. And so here is an ASCII cipher example. And so what this does is it allows you to use other letters in the alphabet. And that becomes important when we go back to protecting stuff like dictionaries, because with the Caesar cipher, you cannot encrypt your curly braces or your colons or anything like that, because it's just doing the alphabet. But this ASCII shift cipher is going to allow you to type in upper and lowercase characters and, you know, basically any of the keyboard characters. So we can try that out real quick. Here it is in the chat. Enter key. I'll just use 5. So we can still do our printable characters, like we could still do the same thing of hello. But we could also do something like a dictionary. My grade slave is showing there. And so we can see, I'll go ahead and paste that into the chat so you can try. Oh, you have to Control-Shift-C. I wonder if I can Control-V it in. Oops. Okay, I don't want to do that. But basically, hopefully you can see from my screen that this dictionary came through as this. And I used a key sequence that tried to take a screen grab. Okay, does that make sense? How it gives you more characters, but also an extra level of strength, and because there's more, you can have more possible keys since there are 90-some characters, printable characters that you could be using.
Do you have an example of a dynamically shifting? So say, for example, you've got 5, but I always loved cryptography. And if you look at this example under result, you see that the comma, just a coincidence based on 5, your apostrophe became a comma.
Yes,
So
yes.
as you start looking at things, there's a lot of repetition, if you will. And I was wondering if there's something that starts at 5, and I'm not trying to go quite as far as the Enigma, but as an example where it's 5, but the next one is 6, the next one is 7 or something like that. And
yeah, let me stew on that, because I think that I've got something, but I'm not exactly sure.
Or using a dictionary or a list to say, or a key phrase that it just follows through. I was just curious.
Well, here's one thing. As far as a shifting cipher, no, I didn't get to. I don't remember having gotten to that point. What I did here, just to keep this within a chapter, I ended it with the @bash cipher, where you're taking the alphabet and inverting it. And then the challenge is to make a custom cryptobit where
That does it. Okay.
But that still leaves open the commonality.
Yeah, the repetition.
Yeah. And so yeah, this has some room to grow. And if it does grow, I think I would want to add that in. But I would also probably just add it in as a module where it does a bunch of different kinds of encryption for you, because I think that we'd be over belaboring the coding point at that, if I went too much further into it. So what I might do is just implement that and then make a module that people can say, okay, now I'll use this encryption, now I'll use that encryption. But we're trying to keep it hackable for the, for a robotics contest. And that at least is the reasoning behind it. So let's see, we've got 18 minutes left. Share something personal. Now we already did the unencrypted smiley faces. And so now let's take a look at the encrypted version. So we'll need to restart with the this script. So I'll paste in the transmitter and receiver. I just pasted in the transmit and the receive, so we want to get this running again. This is the happy, sad, angry sequence.
Is this the same send and receive?
Yeah,
Okay.
I wish I'd saved the corrected one. Okay.
This one's unencrypted, correct?
Yes, so we're starting with unencrypted and we're going to switch over to encrypted, and it's basically just a, you know, a second example of so one of the reasons to have the terminal in effect here comes into play in a while. So of course we can see on the terminal that we've got our happy, sad, angry sequence, and then here we have it on the microbit. Transmitter on the left, receiver on the right. Now, so the students will then switch over to, so this is assuming kind of the in-class experience where we have a transmitter, a receiver, and a sniffer that can all see the same thing. So we have a group of 3. And then we've got the how it works and improving the script, which I don't think I want to do. I think I just want to show what happens when you encrypt one. It's basically going to crash the sniffer's code. So when we switch over to encrypted transmission, so now we're going to do encrypted transmission, and what you're going to get is an error message on your receiver microbit, because we're assuming now that your receiver microbit is the sniffer. Okay, so there is the modified sending script. And when I flash that, we'll see an error message display on the microbit, and we'll also see an error message appear in the terminal. And then, of course, if we give our intended receiver the updated script that is using the Caesar cipher, okay, so there is the receiver script. And so now we're back up and running again. And interestingly, it looks like I do have the code repeating on both transmitting and receiving microbits here. So I'll have to take a closer look at what we're doing. That may have been a your turn section or not, I'm not sure. And so here we got to see, since we only have 2 microbits, not that I'm complaining, it's good that we have 2 microbits. But in a classroom, you know, I would imagine a group of at least 3 here, where one is the sniffer, one is the transmitter, and one is the intended receiver. Because that way they get to see, okay, one crashed. The intended receiver gets to see the, you know, encrypted and unencrypted data, and it works. It's a lesson on an application of that Caesar cipher. Now, the texting with terminals, we did that at the beginning of this workshop session, and I want to point out that the, you know what, I skipped ahead, sorry. Okay, so we're doing this part. There's one extra step, which is, well, gee, the sniffer got a, the sniffer's code through an exception. So they can't show an image that says KDSSB. There's no such thing. And so the sniffer script, the person doing the sniffing will very likely say, well, I don't want my script to crash. So how can I, what can I do to prevent that? And what they can do is end up adding exception handling. And so with the exception handling code, and this is a challenge to them, they have to go back to the exception handling primer and kind of refresh on how to handle those exceptions, as we did earlier, using the try except else finally, and they can modify their code so that they can at least see data coming through and know that it's encrypted. And this actually is setting up for brute force attacks, because we revisit this in brute force, and then a script is used to figure out what encryption key is represented by this data, to talk about things to come. And let's see here, encrypting application data. So this takes us back, oh, I'm sorry. So again, then we did terminals. Now with the happy, sad, angry, we used the Caesar cipher, because those were just all capital letters in the A to Z alphabet. Now, when it comes to chat, that exclamation point wouldn't work with the Caesar cipher. So that's when we switched to the ASCII shift, where we're using all the printable characters. So that's one more step of encryption. And then last but not least, there's application, where we revisit and encrypt the countdown application. And so here is the countdown app transmitter. Okay, I just pasted that into the chat. And then we'll do the app receiver. May have to split this one up into two. Let's find out. Yeah, so this there's too many characters for one paste into the so we're going to need to do this in two parts. So I'll post up to while, I'll try pasting it up to while true for the receiver first. Okay, so that's the first part of the receiver code. And then the main loop.
Why Twitter doesn't work for programmers.
Does it have, oh yeah, Twitter has character limitations. Hashtag give me more characters. Okay, there's the second part. So we'll have to do this in two pieces here. Or actually, I should have done this first. Okay, here's the page. You can just get the two scripts from the page. Okay, so this is the same countdown yet again. But this time, let me verify this. So the key is hard coded as 5 in this one. Now you could add code to make your key selectable, but we're just hard coded on 5 here. So we'll make the countdown start 3, and then the message after countdown can be lift off, secured. And so it traveled through, but the big difference is that this time the data was actually encrypted going out. And using the ASCII shift function. And then it was decrypted coming in using a key of -5. The encryption key was +5. And then the decryption, where is it? Right here. So immediately after it's received, it's decrypted before it's executed.
Can you add in with relative simplicity to say, show me the unencrypted?
Yeah, I'm actually wondering where that is. I may have, let me see if, no, this is just encrypt your app data.
I think if I wrote,
Yeah, we
packet,
really want to see that. Here, hold on, let me,
if we make something like packet 2 equals the ASCII,
well,
equals
all we got to do is say,
the packet.
right here, we can say print unencrypted. And then encrypted. And then we can also do that on the receiver end. I'd really like to use that as actually a your turn, or as, you know, I'd like the students to, you know, my first thought is to have the students do that in some way. Now, where is, okay, so then here's the packet. So they received the packet over the radio. So we'd actually have to put the encrypted right here
Yep.
at the correct indentation. And then the decrypted, whoops. There. This is much better. So again, I'm open to email guidance on, although my first inclination is to challenge the students to display, to essentially go through the process that we did.
I think you meant that second one to say decrypted or unencrypted. And then get rid of the
Oh,
receive.
yeah, so I didn't say unencrypted here. I have a typo. This should have been unencrypted, whereas this is encrypted. So now it shows it going both directions. The unencrypted and the encrypted that's actually sent. Yeah, I'm definitely interested in adjusting that example as you suggest, Alan.
Well, I thought, sorry,
I'm sorry.
just thoughts pop into my head, as I'm
And
teaching this.
thankfully, they also come out your mouth so that we can hear them.
I try to have a filter on what comes out of my head.
And well, everybody's benefiting from this one, I think. All right, so that is just about it for the day. The last thing I have to show you is, so we'll be doing brute force attacks and defenses on Friday, along with hearing from cyber.org and seeing how this all gets added to the Cyberbot robot applications. So brute force is basically going to be a way of trying all the combinations until you can crack the vault code or the cipher or the app or the chat cipher or the application cipher or the robot cipher. And so we'll be talking about this on Friday. And then for your homework, it's not much, and it doesn't look like this. I'll be sending you what it does look like. Stephanie Lindsay updated the email that you're receiving. I think I got some chats that she sent all of you who do not have teacher access to learn.parallax.com. And what I'm talking about here is at learn.parallax.com. So when we go to learn.parallax.com, there's an educator section. And then, for example, we could go to Cyberbot resources, and that's where that's an example. And so we have some open stuff like the scope and sequence. There's no reason to hide that from the students. They're not going to be interested in it anyway. But when it comes to assessment materials, you have to be able to log in order to download them. Because we don't want the students to get the solutions to various exercises that you might be putting in there, or to various things that you might be putting in quizzes, labs, etc. So for those of you who are don't already have a username and log in for learn.parallax.com, you will have received an email from us and from I believe learn.parallax.com. Let's see who it's. Yeah, there should be some kind of account activation. I'm not sure what it looks like now, but it doesn't look exactly like this anymore. I'll send you a screen capture of what it looks like. But basically, if you are not already set up to hit this login and enter your credentials and then sign into parallax.com so you can see the downloads, we want to have you do that by Friday. And so you will have received this email. Now, if you already have a login for learn.parallax.com, just make sure you remember it. Now, if you don't remember it, you can always hit the request new password button. And so that's all we want for Friday. And that is it for this session. Remember, it's the same link that you got when you registered. That same link that you got emailed, you will be using again on Friday. We will see you at 3 p.m. Pacific time, Friday afternoon. And we'll also go ahead and stick around for a while for open discussion. today, but we will go ahead and stop the recording, Jeff.